Okay, so we are live now. So welcome everyone to the seminar in the Statistics Department at the Universidade Federal de Minas Gerais, which will translate to Federal University of Minas Gerais in Brazil, UFMG. So today is a great pleasure to receive here Richard Hahn, which studied together with me some years ago at Duke University. So basically, some few details about his academic path. He got his bachelor degree in economics from the Columbia University, a Master of Science in Mathematics in New Mexico Institute of Mining and Technology, a PhD in Statistical Science at Duke University. And today he has a position as an associate professor of statistics in the School of Mathematical and Statistical Science at the Arizona State University. And Richard published many research in important statistical papers in statistical journals. So you can see more details in his CV, which is available in his personal website. And he works in several research areas in the field of statistics, including Bayesian methods, causal inference, regression trees, machine learning, semi-supervised learning, latent variable models, application to social, behavioral, and health sciences. So lots of fields. And Richard, thank you very much for accepting my invitation and being here with us today. So you may start your presentation. Thanks again.
Thank you. That was a really nice introduction. I appreciate the invitation. I miss talking about research. I used to give a lot of talks, and since the pandemic, I've been giving less, but these Zoom talks or these broadcast talks are pretty nice. Please jump in with questions if you have them. There's a little bit of a lag, but you guys should be able to see what I'm doing. So the topic that I'm going to talk about today is something really classical in some ways, and it is the use of control variables in a regression model to figure out a treatment effect. So the treatment effect that we might be interested in is, does a certain vitamin improve health outcomes, or does a particular institutional policy improve revenue, or treatment in the broad sense where you want to do something and you want to see what happens because of that. And we all learned in intro statistics that if you don't control for the right stuff, that you don't get the right answer, and we call this confounding. And typically the way that it's taught in an introductory class is sort of in the context of linear regression, and controlling for a variable just means including it. So in other words, do you include it as a feature in your regression model? So what this talk is about is a big chunk of it, most of it probably is expository. And I'm just going to be talking about three different frameworks to understand the issue of confounding and the solution to that, which is called statistical control. And so we're going to talk about how to make sense of that. So in the linear regression model, you can do a direct calculation, and you can find out that if there was a variable that you forgot to include, that you'll have a biased estimate of the regression coefficient. And that's pretty much in an introductory level where it kind of stops. And it's unfortunate because that's a little bit misleading. And the reason that it's misleading is that there's nothing about linearity that's critical to this idea. And it's not really about parameter estimation. It's about this idea of treatment effect estimation. And so the first thing we have to do is we have to define what we mean by a treatment effect, because if a treatment effect is not a parameter in the model, then what is it? So the first step is to define what we mean by this causal estimand, causal meaning the cause of the treatment. The treatment is causing a particular outcome. Okay, so that's the big problem. And then the smaller problem, the sort of sub-problem in that is that we're tackling here is, let's assume that we have all of the relevant variables, that we have a rich enough set. People at that point often want to do variable selection. So variable selection is probably the most popular topic in all of statistics in the last 20 years or so. And there's lots of different reasons why we might want to do variable selection. So one reason is just that we're curious. We want to know which variables are necessary to identify a treatment effect. But the other reason is for variance control. So we might want to do variable selection because we have too many features. And if we didn't have to use all of them, that would be good because we would get a more precise estimate. And that's the problem that I'm going to be looking at today, is like the end goal here is just to get a nice statistically precise estimate of some treatment effect, some causal effect, right? A policy evaluation. And I have a lot of variables to do that with, and I might not want to use all of them, but it gets real tricky, right? Because if I don't use enough, I actually have a biased treatment effect. So that's a whole bunch of talk, but hopefully it sets the stage. And now we're going to talk about the three most common frameworks for making all of these definitions precise. Okay, so for a couple of different reasons, not all of which are shameful, I'm going to be using the actual paper text as my sort of guide during this talk. And I'm going to annotate it as necessary. This is joint work with my awesome student, Drew, who is here with me at Arizona State University. And we've been working on this for a while now. So shout out to him, and I'll kind of point out some of his major contributions to this work. Okay, so in terms of the problem statement and the notation, we are going to refer to Y as our outcome variable. And in general, you can think about that as a continuous variable. We are going to have a binary treatment assignment. So the treatment, did you get treated or not? I'm going to call Z. And then X is going to be a big vector of covariates that are drawn from some space. The case that I'm focusing on in this paper is a simplification, mainly for clarity, which is that I'm going to assume that my covariate space is discrete. It doesn't need to be ordered or unordered, but I'm assuming that the covariates have distinct values that I can look at. If you have a continuous covariate, you can discretize if you need to. And the data is going to come to us as independent draws from this triple, which is the features, and then the response variable, and then the treatment assignment. More generally, a treatment assignment can be a dose, right? It could be how much of a drug did you get, or how much of a tax break did you get, or whatever the treatment of interest is. For simplicity here, we're going to be talking about binary treatments. You either were in a treated group or you were in the untreated group. The basic problem of confounding is that if you just did a comparison of the people in the treated group and the people in the untreated group, they might be different in other ways. Okay, so if it's the case that the sort of the units that got treated are systematically different in terms of their response than the people that were untreated, then when you look at the averages in those two groups, they're going to be different anyway, even if there was no treatment effect. And so confounding in this case is a matter of non-uniqueness, right? We don't know if the difference between those two groups is due to the fact that one was treated and one was not, or if it was due to sort of other stuff. And the way statistical control works is a process of elimination. We would like to eliminate all of the other factors that might be contributing to that difference, so that anything that's left over must be due to the treatment assignment. Okay, and that's why that's why it's referred to as statistical control. And the idea really goes back to the scientific method. We want to hold everything else constant, right? And if we held everything else constant, so that the only thing that was different was whether or not you got the drug or not, then that contrast can be interpreted causally. Okay, so in some sense, it's a very simple idea, but the devil is in the details, which is how much stuff do you have to control for, which is sort of always the issue. So now I'm going to run through three different perspectives, sort of really just three different formalisms notations for how to think about this. And one of my main goals is to convey that these things are really doing the same thing. Okay, there might be some technical details that are not common between the three approaches, but I want to emphasize the commonalities because basically in most cases that we're interested in, they are effectively the same. So what are those three cases, the three frameworks? The first one is potential outcomes, which is attributed to Don Rubin among a few others. The second one is causal diagrams and the associated functional causal models, and that work is associated with Judea Pearl. And then the last one is in some ways actually the oldest one, and it is the idea of endogenous and exogenous errors and structural equation models coming from econometrics. Okay, so I want to briefly introduce each of those, and then I want to show you that they're the same. So the potential outcomes framework is very nice because it really puts the problem in stark relief. The idea is that there are two totally separate states of the world, one in which a unit received the treatment and one in which it did not. Okay, and you can think about conceptually each of those as having an independent existence. And when I say independent, I mean it in the colloquial sense. Okay, meaning that it's a bivariate quantity. Okay, and we refer to those with superscripts in this paper. And so Y superscript 1 means the outcome that would have happened if the unit had been treated, and Y0 is the outcome that would have happened if that unit was not treated. And we can think about those as having an existence, but we only get to see one of them. And that was Rubin's insight, which is that we only get to see one of those things at a time. The thing that we want to estimate is the difference between them. The treatment effect is the gap between what happened under treatment and what would have happened under control. So sometimes these are called counterfactuals. I just like to think about it using a term from linguistics, which is subjunctive, which is the would have, what would have happened, right? Okay, so the way that potential outcomes, in some sense, the potential outcomes framework is as simple as just introducing notation to make clear the fact that these are two independently existing quantities. And then what we can do is we can relate those to the data via an equation where the observed treatment variable, which is z, is essentially gating which one we see. So if z equals 1, then the y that we observe is the y1 potential outcome. And if z is equal to 0, then we see the y0 potential outcome. So we only get to see one at a time. And this is why causal inference is sometimes referred to as a missing data problem. With that notation, the estimand of interest, the thing we want to estimate, is in this paper, and in many cases, it is the average treatment effect. So the expectation here is over a population of units. And we want to look at the expected difference between those things. So the difference is the treatment effect, and then the expected value is the expected difference, and we call it the average treatment effect. Okay. Now, because we only see one or the other at a time, we need some assumptions to make this work. And the assumptions we're going to be working with today are fairly standard, and I will quickly talk about them. The first one is called Satva, the stable unit treatment value assumption. And the idea here is that the treatment assignment can only affect the unit that it is ascribed to, right? So the way that I always like to think about this is students in a classroom and the treatment variable being tutoring, okay? And the idea is you want to see whether or not tutoring is affecting a student's progress, but that might be a Satva violation because these students have social relationships and they're friends and maybe they study together. And so whether or not Bob gets tutoring might help Sally regardless of whether or not she did. So that would be a violation of this, this sort of sometimes it's called no interference assumption. The second one is positivity. It needs to be the case that everybody has a chance of getting the treatment. If there's regions of feature space where there are certain individuals that can just never receive treatment, or never receive or never not receive treatment, then we can't estimate the contrast that we want. Those two assumptions I'm going to assume throughout, and those are sort of background for us. The key one that we're going to focus on today is this conditional unconfoundedness. And conditional unconfoundedness says that the potential outcome random variable, so that bivariate random variable, has to be independent of Z given some particular set of features. Okay, and in the case that you have a randomized trial where Z is assigned by tossing a coin or by running a random number generator, then that will be satisfied without any features at all. On the other hand, in observational studies, it might be the case that given a rich enough set of control variables, that independence is satisfied. So if this is your first time seeing this, then that condition on the one hand might seem kind of obvious if you have some intuition for how randomization works. On the other hand, it might seem a little bit confusing as to how we would ever go about evaluating that other than in a randomized trial. And that's really what this talk is about. The idea is, if we have an X that we say satisfies that, are there subsets of X that might satisfy that or not? And how do we think about that? So the way that this works is that if these three conditions are satisfied, then you will be able to estimate the treatment effect via the following identity. And let me unpack this a little bit. But the idea here is that this term is the conditional expectation of the treated units, and it's conditional on the treatment assignment, Z, and also on X, those features. And what ends up, the way that this works, and this is where I will try to write this, the idea here is that the expected value of Y given X, Z is equal to 1. Wow, that looks terrible. That is equal to the expected value of Y1 given X, okay? And the way that that works is that follows directly from the conditional unconfoundedness assumption. Because if you assume that if you have X, then Z is independent of Y1 and Y0, then you can use the fundamental identity there to find that the observed conditional expectations, in fact, allows you to estimate the counterfactual or the potential outcomes differences, which is what we want. So mathematically speaking, it's all very straightforward, and that's it. That's the extent of it. I just showed you the equations, and if you make that assumption there, then the right-hand side here is something we can estimate from data, and those assumptions being satisfied gives us the equality written in green, and everything works great. Okay. The thing that is left unanswered by all of this is why, right? So how do we know? Stating 3 as just a condition straight up seems a little bit like you're begging the question. You're just assuming that you have the things that you need, and then you can go ahead and estimate it. By the way, if your model is linear, then you can estimate these conditional expectations with a linear model, and the difference here will be represented as a coefficient. More generally, we have modern tools to estimate conditional expectations. And so that's sort of how this works. So that's the potential outcome setting. And there has been some thought, a lot of previous research about the question, can I do better than just X? Like, is there a subset? Is there a transformation? Do I have to use all of it? So one of the earliest papers is the propensity score paper. So the propensity score, which I did not define here, the propensity score is the probability of receiving treatment. So in this talk and in this paper, we're going to refer to that as pi of X. So that's the probability that Z equals 1 given X. Turns out that that's enough. So you don't need all of X. The propensity score is enough. Okay. There was a later paper in 2008 that says that if there's actually no treatment effect heterogeneity, then another variable, another dimension reduction that works is the conditional expectation of the control group. Is actually something that if you knew that function, that would also be a sufficient control. Okay. So that's it for potential outcomes, and it works great and it helps clarify things, but it also leaves a lot unaddressed. So what Pearl's work does is it tries to take a more granular view, and it tries to think about which variables are necessary based on the causal relationships between those variables. Okay, so if we knew the relationships between x1, x2, x3 up through xd, then we should be able to use that to tell us something about which variables we need to use. Now, on the one hand, this solves the problem I was complaining about a minute ago, which is that just declaring that something satisfies conditional unconfoundedness seems like a miracle. On the other hand, now we have a really tall order, which is that we need to understand all of the causal relationships between all of the variables. So let's start out with a simple graph here, and let's talk about what these graphs do. This is going to be a very quick primer. If I had more time, I could describe this in more detail, but let me just try to give you the flavor of this. So the goal, what is the causal diagram? So a causal diagram is basically two things. First of all, it's a directed acyclic graph. So directed means that the arrows, the edges have arrows, so they're directional. Acyclic means that I can't go in a loop. So there's no way to traverse these arrows in the correct directions and sort of loop back to itself. So that's the graph theory side of it, which is not actually that interesting. The interpretation is what's interesting, which is that we want to interpret these arrows causally. And by that, I mean, we want to think about this as a mechanistic system where if I change the variable x4 in this case, that will change the distribution of y. Okay, so again, you know, we're thinking about this counterfactually, or it's sort of like the potential outcomes, right? In the world where I changed the value of x4, what would be the corresponding value of y? So we can think about the arrows here as describing functional relationships that are deterministic, not stochastic, okay? And then what we observe has some additional randomness. Okay, so if you think about it that way, what these arrows are doing is that they are specifying a decomposition of the joint probability distribution. And they're decomposing it into a product of terms where each of the terms is a conditional density, okay? And so in this particular example, the joint distribution, let's go ahead and write it out. So f of x1 is independent of f of x4 is independent of f of x3 is independent of x2. Don't know why I didn't do those in order, but we've got 1, 2, 3, and 4. How do I know that they're independent? Because they don't have any arrows between them, and they have no arrows coming into them, okay? Then for every variable that has arrows coming into it, the in arrows are the things you have to condition on. So we then have f of z given x1, x2, x3. And we have f of y given z and x1 and x4. Okay, so the product of those terms is the joint density, okay? Now, just like in the potential outcomes, this is just a formalism. This is just a way to, you know, but there's more going on here, because instead of just explaining the relationship causally between x and, you know, between z and y, we're now having to explain all of the x, z, y relationships, But if we're able to do that, we get a lot from that, which is that we are able to figure out subsets of variables that satisfy strong ignorability. So the way that that works in this graph context is, as I was saying before, we are interested in the causal effect. But in order to find the causal effect, we need to rule out all of the other things. And in particular, we have to rule out the fact that Z and Y are related via some other route. So we refer to these as backdoor paths. So there's a relationship induced between Z and Y due to X1, and there's also one due to X2. And so if we just took the naive contrast, we would not be able to distinguish what was due to the treatment itself and what was due to these other associations. And so the idea of statistical control is that, well, if we knew the value of X1 and X2 in this particular case, then we would be able to rule out those paths, and we could then interpret this as, we can interpret the difference causally, the way that we want to. So the way that we're going to relate this to the potential outcomes is via this idea of what I will refer to as a functional causal model. Sometimes you will hear them called structural models. That term typically means a linear structural model, so we're going to call these functional causal models. And the idea is that the graph is encoding the causal relationships. And so if we think about the distribution for Z and Y, then we can write them out as follows here, with these independent error terms. Okay, so what this means is that as a function of X, the distribution of Z is going to change. But then we can think about the randomness in Z as being due to this error term, epsilon Z. Likewise, we can think about the distribution of Y as being functionally deterministically determined by the values of X and Z, with then some error coming through another independent error term, which we will call epsilon Y. Okay, so what the graph does is the graph tells us which of the variables are going to appear in this function. So in the case that we just looked at, although I have it written here in terms of the vector X, we saw before that it was actually only X3, X1, and X2. So X4 does not play a role in the G function here. And likewise, X3 does not play a role in the functional model for Y, okay? So if it's, yeah, okay. So that's how those two things relate to each other. And more specifically, what this means is that we can think about the potential outcomes as being mapped to these things exactly via that function f. So if I tell you all of the values for x, and then I set z equal to 1, by definition, because I'm thinking about this f as being the deterministic piece, that will determine the value of y1. If I switched it to 0, that would then be equivalent to y0. Okay, so in some sense, if you've got the graph and you're willing to write down the graph, then that gets you the potential outcomes using this idea of a functional causal model. Now, that relationship might seem trivial, but here's really the first thing that is not maybe strictly review if you work in this area. So the first thing I want to point out is that this epsilon y that appears in this, that can actually be bivariate. Okay, it could be higher dimensional than that actually, but it can be bivariate, right? So as long as epsilon y is independent of all of the x's and z, then I can write down the model this way. It can be multivariate. And in particular, you can have interactions between x and z and epsilon within that function, right? So, and you can, and the values of x can pick out different things. All of which is to say, many times in potential outcomes, we think about the potential outcomes distributions as having maybe different variances. Okay, so the Y1 potential outcome might have more variance than the Y0 potential outcome. Those distributions can be totally different that way. That can be accommodated in this case, because what you can do is epsilon y can be multivariate, and which value of z that you observe can pick out which of the two error terms. And those error terms, those elements of epsilon y can have different variances. Okay. For example, the other way that shows up, lost my train of thought. It can be bivariate, and so they can the elements of epsilon y can actually be dependent, and what that means is that the potential outcomes distribution, the y1 y0, can actually also be correlated, for example, and if they're correlated, that's fine, nothing breaks. Okay. What's interesting to sort of keep in mind is that whether or not they are correlated, we can never tell from data, because we only see one thing at a time, right? So the reason we can estimate that average treatment effect is precisely because expectation of the margins, the y1 and y0 potential outcomes, those expectations are not affected by whether or not the random variables are correlated or not, which is one of the remarkable properties of expectation. Okay. Now, the real where Pearl's framework really gets moving is in this idea of whether or not we can find subsets. And so, returning to this example here and clearing off some space. Okay, if you look at this graph, and I just want to think about this intuitively for the time being, we probably don't have to control for all of X. And in particular, the thing that I don't have time to talk about today, but one of Pearl's major contributions is that he specifies an algorithm that tells us, if we have the graph, I can tell you different subsets that will satisfy conditional deconfoundedness. So in this particular graph, I will just tell you, X1 and X2 are enough. I don't need to condition on X3, and I don't need to condition on X4. And I think, and hopefully you think that's kind of intuitive, right? Because the path from X3 doesn't connect Z and Y. And so the two paths that in this case that we have to worry about are just X1 and X2. In more complicated structures, it gets more complicated. But the algorithm is provable, where you can figure out on the basis of the graph whether or not a set satisfies conditional deconfoundedness. And the way that it basically works is it says, imagine that this thing were not there. Okay, if that causal link were not there, then we would need it to be the case that they were independent, right? Because if there was no relationship between Z and Y causally, and there was still a relationship, that's exactly the relationship that makes us unable to figure out the causal effect. So what we want to do is we want to find a set that renders Z and Y conditionally independent in the event that there was no treatment effect. And so that's essentially what the algorithm does. And so that's a good starting point for us. So what do we have so far? If we start out with the idea that X is adequate, then we know we can condition on all of X. If we know the propensity function, then we can condition on level sets of the propensity function. That was the result of Rosenbaum and Rubin 83. Hansen in 2008 said that we could condition on the level sets of the prognostic function. And then Pearl says that we can also find these subsets as long as they satisfy the so-called backdoor criterion, which is that they deconnect Z and Y. Okay. So that's really good. And furthermore, we can think about those results in the context of the graph now. So one thing that we can do is we can say, well, what is the propensity function for a graph like this? Well, the propensity function is exactly the function that takes in particular values of X1, X2, and X3 and spits out and spits out a probability, and that should be enough for us to know. Because if we knew that, then that would cross out all of these relationships. This thing is adequate. So that's what the propensity score says. In the case that we have homogeneous treatments, the expected value of y given x and z equals 0 cuts off all of those arrows. Okay, so in other words, those earlier results can be phrased in terms of Pearl's criteria as being a sufficient statistic that satisfies the backdoor criterion. Okay. The last thing is the third approach is this idea of structural models with additive errors. And this is where I think things get really interesting. Okay. So what we're going to do is we are going to think about the expected value of the y0 and y1 potential outcomes. Okay. So in other words, if we have a functional causal model denoted here by capital F, and we have the value of x that has been observed, and we're going to then integrate over the exogenous error, the independent error, this epsilon y term. We can define that, and let's call that mu of x. Okay. With mu of x in hand, we can then talk about the y1 potential outcome, which is this second line here. And we can think about that as being mu of x plus tau of x. Okay. And that's just to say that the treatment effect here is exactly tau of x, right? The expected difference between y1 and y0, we're denoting tau of x. So that's nice because that now gives us something like a parameter. We can now refer to tau of x, and that is the treatment effect, the average treatment effect for a unit that has these particular features. Okay. And the name for that is a conditional average treatment effect. So tau here, we can think of as the conditional average treatment effect. Okay. Furthermore, we can take the actual value of the potential outcome, or the evaluation of the functional causal model, and we can subtract off the mean. And we can call that thing epsilon, or v. It kind of looks like a v here. Likewise, we can take the actual the actual treatment effect, and we can subtract off the average treatment effect, and we get these error terms. Okay. So all that I'm doing here is just manipulating some of the definitions that we've had before. But when you do this, you get something really nice, which is now you've got these functions and you've got these error terms. Okay. And the functions are conditional expectations, and the error terms are by construction mean 0. Okay. So for every value of x, the way that I've defined this, the random variable epsilon has expectation 0 integrating over epsilon y. Likewise for delta. Okay. When I do that, I can then rewrite y in terms of this so-called structural model. And so this is why I'm reserving the term structural model for this, because this is the term that is used, which is y is equal to mu of x plus some error term plus tau of x plus some error term times z. Okay. And because of the way we defined all of these terms, equation 6 there is just an identity. But we are now in a familiar framework for anybody that is used to doing mean regression modeling. Because when you do mean regression, you think about the expected value as a function of x, and you think about the error terms as being mean 0. Okay, and now we have that. One of the things, so I should also mention that this is typically used in a simplified form where the delta term is assumed to be 0 tau is assumed to be a constant, and then you just have one error term, which is this guy right here. Okay, so my claim is that the following three statements are equivalent, and this is the status of this proof right now is a little bit heuristic, but let's talk about it. So the usual potential outcomes thing would be to say that X satisfies conditional unconfoundedness, which is just written in the notation that I have there. If you're used to working in the Perl framework, you might say X satisfies the backdoor criterion, and therefore the functional causal model can be written in terms of these independent error terms. And if you're used to structural models with additive errors, the way that you might think about it is the error terms are independent of treatment assignment given X. But if you think about it, these are all the same thing. So because of the equivalence between the functional causal models and Z, we can write Z is equal to G of X times epsilon Z. We're going to use our structural model to write out the Y potential outcomes. And so this block of equations in 7 is just basically setting up the structural, like the equivalencies between these, okay? When you do that, then we can step through those terms 1, 2, and 3, and we can talk about what they mean. So in particular, if you look at Y1 and Y0 in terms of the structural causal model written right here, you will see that the only randomness, so conditional on X, if I know the value of X, the only randomness here is due to epsilon Y. And the only randomness in Z, given X, is due to epsilon Z. Therefore, statement 1 is true if and only if those error terms are independent. The error terms being independent is a restatement of 2, because satisfying the backdoor criterion is exactly what allows us to write down a functional causal model with independent errors. And the kind of more interesting one is if you look at those two error terms, the epsilon and delta, they also only involve epsilon Y. Okay, so 3 different ways of doing the same thing, right? In every case, the idea is we want to somehow say that if I know X, there's no systematic variation between Z and Y. And the way that we can do that is we can talk about error terms, or we can talk about functional models with independent errors, or with independent innovations, those epsilon Ys, or we can think about the potential outcomes. And you know, in the case that we're looking at here, there is no major difference. It seems like there might be a difference, right? Because the way that this ends up looking is a little bit different than standard. But I would say that that's mainly just a matter of convention. So in econometrics, you typically don't think so much about treatment effect heterogeneity, and you maybe don't think about, you certainly are not worried about confounding due to moderation, typically, in my experience. So in other words, the fact that this thing, you know, that thing doesn't normally appear in textbooks, okay? This thing normally appears in textbooks, but it normally appears just as an error term. And the claim is that that is independent of Z, okay? So it's a little more complicated to make them the same. Likewise, in the potential outcomes framework, people think about, because they think about Y1 and Y0 as just a bivariate random variable, it's sort of obvious that those things can be correlated and that one of them might have more variance than the other one. Whereas when you think about the functional causal model, it's tempting to think about that error term as deterministically changing Y, you know, the observed value of Y. But again, once you recognize that the epsilon Y can be multivariate, you realize that you can get back sort of in all generality the potential outcomes setup. Okay, so I knew that there was a lot of stuff, and if you haven't seen any of this before, maybe hopefully this was food for thought, and I didn't waste anybody's time. What I'm going to do now is I'm going to do 10 minutes worth of the new stuff using these ideas that we have just set up. and make a couple of concluding points, and then we'll have to end it there based on time. So the first thing that we might want to think about is, if I'm only interested in the treatment effect, do I really need to satisfy conditional? Conditional deconfoundedness is phrased as an independence assumption, right? And it turns out that the independence assumption is actually a little bit too strong, okay? So all that we really need is mean conditional unconfoundedness. And the definition of that is that Z has to be independent of mu x tau x, given that function, given the control features. The way that this works, so recall the definition of mu and the definition of tau. Tau is the treatment effect as a function of x, and mu is the prognostic value, meaning it's the value that you would expect for y without being treated. And those two things basically tell you everything you need to know about the mean of the potential outcomes. And the mean of the potential outcomes is the only thing that we're trying to identify anyway. Okay, so if you write down this weaker condition, you can basically show that that is going to get you what you need. And the way that it works is via the structural equation that we wrote down. So the structural equation turns out to be a very powerful way to think about some of these issues. So if you write down the structural equation and you remember that those epsilon terms for every x are mean 0, okay, then you can think about writing down the potential outcomes conditional on some covariate set using that expression, okay? And because we can write that in terms of, so what am I trying to say? We have mu and we have tau, and we also have this epsilon and this delta, okay? The mu and the tau are going to be independent of Z. The epsilon and the delta don't have to be, but by construction for every x, they have mean 0. And what that means is that even if they're not independent, when we take that expectation, those terms are going to vanish, okay? In other words, and it should be kind of obvious if you think about it, what we really need is just, we need it to be the case that this expectation can be interpreted causally, okay? So I guess, so one way to think about this is there can be dependence between Z and those error terms, but not in the mean, right? So in other words, you could have, as I was saying before, you could have different levels of heterogeneity in Y1 and Y0, and that would be fine, as long as the mean is not being affected. So this is now the case where you sit back and say, oh, the structural equations econometricians sort of had a point, which is that, you know, they didn't have to assume something strictly stronger. They just said, assume we can write down a structural equation that has this particular property. However, and this is the thing, this is sort of like probably the close to the last thing. Mu and tau here don't have to be interpreted causally. And that's a little bit weird. At least when I learned econometrics and I heard about structural equation models, I didn't think about them formally as just assume that it's an equation that has the property that the error term is independent of Z. I mean, obviously that's all you need, but the terminology and the conceptual way that they're normally presented, it's tempting to think about the mu term in particular as being deterministic, meaning if I change X, then Y is going to change causally. But you actually don't need that. That's actually stronger than you need. And I'll show you an example shortly where the mu function is certainly not causal, and it doesn't matter, right? Now that we have this idea of mean conditional unconfoundedness, right? So this is going to be the new stuff that we do in this paper, which I won't have time to talk about much, is based on this idea, okay? Well, we want to think about a function mu and tau of X, and then we want to think about some other function of X that decouples it in the sense of Pearl, basically, from Z, okay? So one way to think about this now is that the graph that you draw when you draw a causal diagram, you can, if you're only interested in average treatment effects, that graph only has to represent the functional causal model for the mean. If the arrows are only affecting the epsilon and delta, you don't have to draw them because they don't mess with the expectation. I think implicitly, because people are used to doing mean modeling all the time, that's often how they think about it anyway. But strictly speaking, you can have a graph that has a lot more arrows in it. But if those arrows are only affecting the distributional shape of the error terms, you can actually get rid of them if you're only interested in average treatment effects. Okay, so the last thing, and I think it's the cool thing, is that this now allows us to start thinking about a way to define the minimal number of controls that we might need. And so to that end, I am going to define this thing called which we call the principal control function. So assume that you know the function mu of x and tau of x and pi of x, okay? If in practice, if you knew all of those things, you would obviously be done because you could read the treatment effect directly off of tau, okay? But conceptually speaking, it turns out to be very useful to imagine this, to think about this particular expectation. So it's the expected value of the propensity function given the mu tau, so the prognostic function and the treatment effect function, okay? So if you think about it, you don't need to know, x might be high dimensional. And what we're doing here is we're integrating over the unknown values of x, fixing particular values of mu and tau. And then we're taking an average of the propensity function, so how likely you are to get treated. So we're going to call this quantity lambda and call that the principal control function. With that definition, we have the following theorem, which basically copies the proof of Rosenbaum and Rubin 83 about the propensity score, which is by iterated expectation, the treatment variable given mu and tau is a Bernoulli random variable that has probability lambda. And therefore, lambda is all that you need. In other words, if I told you the specific value of mu and tau, you don't need to know that. All that you need to know is the corresponding value of lambda, because lambda, the probability, z is a 0-1 variable. So the only thing that defines its distribution is that probability. So the particular values of mu and tau don't matter. All that matters is lambda. And that's a definition of independence, right? Is that the conditional distribution, it's conditional independence. If I tell you lambda, mu and tau doesn't change the distribution. That being the case, then you can look at the observed conditional expectation as a function of lambda, and you can rewrite it in terms of being conditional on z. And so the next 3 lines of this basically just show you that you can then interpret that as the potential outcome expectation, which is the thing that you need, okay? The more interesting thing is that it's minimal. And the reason that it's minimal in the following sense, there is no other function of x that is coarser than that, that satisfies the necessary condition. In other words, mu and tau, we know those mu and tau satisfy strong ignorability. They chop off all the arrows on the y side of the graph. The propensity score, pi, chops off all of the arrows on the left side. What this is telling us is that there is an intermediate thing potentially called that we're defining here as lambda, which is potentially coarser than either of those. Okay. One particularly interesting instance of this is the last thing that I will show you. And I will actually just show you a picture because this picture changed a lot about the way that I think about these problems. So imagine that you have an x variable that takes on 31 values. And you know that if you condition on all 31 of those values, that you can learn the treatment effect. But what we have been talking about is that you don't actually need to control for all of those. We could do the propensity score, we could do the prognostic score potentially, we could do the, sorry about all the scrolling here, I don't know what's happening. It will catch up hopefully in a moment. So the question is, can we get by with less? And so let me just show you this picture. So X takes on 31 values, unique values. Pi takes on 10 unique values. And in this particular case, we're gonna assume tau is constant, and mu takes on 10 unique values. So in other words, if we condition on all of X, we have to condition on 31 things. If we condition on pi of X, we have to condition only on 11 things. And if we condition on mu, the prognostic score, we have to condition on 11. But we can actually go less than that. And the reason is that we only, as long as one of those two things is constant, we've controlled all of the variation. So in other words, one way to control systematic variation is to just get rid of all variation. Okay, so the picture that I'm showing you here is the gray is the propensity function, and the black is the prognostic function, mu. And as you can see, the region on which pi is varying is the region where mu is constant. And the region where mu is varying, pi is constant. And so all that we actually need to know is which of those two regions we are on. And so it turns out that a adequate deconfounding set for this example is actually just the indicator variable of whether you're less than or equal to 10. The reason that this all pays off is that when you are estimating these treatment effects, using more things or less things can help your statistical accuracy. And that is the portion that Drew worked on. And unfortunately, there's just too much here for me to talk about. I spent too long with the review. But what the picture is showing is the sampling distribution for different control sets. So green is mu, orange is all of X. The red is the coarsest one that is adequate, which is just the two-level variable. And then pi is the propensity score. And what you basically see is that the mu one is actually the best because knowing the prognostic function helps reduce variance. X in this particular case is strictly over-stratified, but because it still conditions on the levels of mu, it is doing a good job. The coarse one is then the next best. And the worst one is the one that controls for all of those unnecessary prognostic variations, because those neither help predict Y, nor are they necessary for confounding. The rest of the paper is about how to use the idea of lambda to try to figure out a method, essentially, to give you a control set that will make sure that you're sort of in the sweet spot using stratifications that are good enough to learn the treatment effects, meaning they're not confounded, but increase your statistical precision, basically. Okay, I am very sorry that this went this long. I didn't get to the stuff that I think is really cool, but hopefully that review was sort of interesting to some of you. I got a question here.
You have a question from Enrico.
Yeah. In the case of a clinical trial where you have been randomized, you technically don't have to control for anything. And in that sense, the three frameworks are sort of, it doesn't really matter. They all say the same thing, but they basically say you can just take the group, the treated average minus the untreated average, and you're fine. And that's true. If you have variables that are predictive of the outcome of interest, it can be of benefit statistically to control for them. So you can still do stratified estimators after randomization. one of the things in this paper that we do is we have a theorem that basically says when that is the case, like when is that beneficial. And unfortunately, the conditions under which it's true, we never know, right? Because we don't know the data generating process. Nonetheless, it's instructive because there's been a lot of debate among people that do this kind of work about exactly this. If we've randomized, should we bother controlling? And the brief answer is like, yeah, like sometimes. If there is a variable that is highly suggestive of what that level will be, taking that into account will dramatically reduce the variability in your estimator, basically.
Okay. There is no other question here, but people, anyone can ask a question in the chat of our YouTube channel, and even in Portuguese, I can translate for Richard. I have a question, Richard.
Yeah.
When you describe at the beginning of a presentation the variables, you said that Z should be binary. Any thoughts about Z being having more than two categories, like three categories?
So all three of the frameworks can handle that. The conditions are the same. It is harder to prove the variance results, which is, so there's basically two reasons we focused on the binary case. One is because in terms of the exposition, it's much easier to do things rigorously in the case where there's only two. And also, 80% or more of studies are sort of in that framework, but there's really no obstacle to, all of these ideas work just as well when there's multiple levels of treatment, but the potential outcome distribution gets to be much higher dimensional. And consequently, the conditions are harder to write down,
Okay. And in figure 2, when you show the graph and the relationship between the variables, so when we think about doing this in practice, because you said something about this relationship should be known. So in practice, how do I determine this relationship, or I have to talk to a specialist to establish that?
Yeah, to use the graph sort of to its fullest possibility, you should know it. If you don't know it, you can try out different graphs and sort of do a sensitivity analysis. There's a whole field called Causal Discovery, which is the idea of trying to learn the graph from data. The problem is that in all generality, the thing you have to do that is a whole bunch of pairwise independence tests for which you need huge amounts of data. And so in practice, in the work that I do, I don't really trust causal discovery very much. What this paper is about, though, is that we're going to try to use the ideas of the graph to help us come up with methods that will allow us to not have to specify the graph, if that makes sense. So the idea is I want to start out with the assumption that X satisfies conditional deconfoundedness. And then I want to develop an algorithm that will allow me to penalize larger models in a way that doesn't introduce bias. And the way that we end up doing that is that the graphs become a mathematical technique for us to do those proofs. So we end up using the graphs a lot, but we end up doing it on the methodological development side as opposed to the application side. So when we go to do the application, we actually don't have to specify the graph. But the graphs are very, very helpful when you're trying to talk about whether or not a particular algorithm will satisfy the type of unbiasedness that we want.
Okay. And when you talked about equation 3, you establish an equality between C and the graph, and then you include in your notation the epsilon Z. Would that indicate some, I don't know, some sort of uncertainty about the graph? The presence of that. I mean, I worry about the presence of the epsilon, I mean.
No, so the way to so remember that the graph is just describing a decomposition of the joint distribution.
Yeah.
And so each of those nodes is actually still a random variable.
Okay.
And so what the epsilon term is doing is the epsilon term is essentially the lag here is incredible. I'm sorry on the pictures. You can think about each of these graphs as having their own exogenous errors that we just suppress. So the larger graph that includes the independent errors is deterministic. But typically we suppress those, and then just think about it as describing a decomposition of a joint density, or
Okay.
Mass function. Yeah, that's a good question.
Well, so let me see. I took some notes during your presentation. Yeah. Now my final question is related to the equation 5 or 6. I guess I'm not sure about the number, but it's 5 or 6 where you establish the y equals to mu of x, and then you have two error terms, right? The epsilon and the delta term.
Yeah.
You talked about the mean 0, but is that any idea or anything to say about the distribution of these errors?
No, I mean the way that I structured it in this paper is basically I wanted to set aside all of those distributional questions to focus on the mean. What this means, and I have this somewhere in the text around here, but what it means is that the mean conditional deconfoundedness is not enough to estimate like quantile treatment effects, right? Because to estimate quantile treatment effects, or to estimate the distribution, the change in distribution of the potential outcomes, you would need to have those stronger conditions.
Okay.
Which is that you would need the error terms to also be independent.
Okay.
Yeah.
Well, that's all my questions. So in the chat, people are not asking anything else. So I guess we can end here your presentation. I would like again to thank you for your time, for being here with us, making this presentation. I will just ask you to stay a little bit more, just to say goodbye here. I will just to finish the presentation with the audience. So thank you, everyone. I will just say that in Portuguese. Pessoal, então no próximo seminário a gente vai voltar com a apresentação da professora Rosângela, que vai dar o próximo seminário na sexta-feira, dia 14. Então até lá e obrigado a todos por assistir. So thank you, Richard.
If anybody that has seen this wants to talk to me about it, please email me. Like I said, it's a work in progress right now, but I'd love to talk.
And if you'll have a few words about your PhD program in your department?
Other than just, go check out our faculty, and if anything we're doing looks interesting,
okay.
Drop us a line.
Okay, so thank you.
Yeah, thank you.